So this is about energy. And I want to talk to you about what the challenges are that we need to solve through research and through innovation and through industrial application. So my connection to the previous talk is to tell you what it is we need to, what some of the problems are we need to address. I'm going to do this in three parts. First, I'm going to give a very brief framing of the grand energy challenge in front of us. Then talk a little bit about what we're doing today and have been doing in recent years to address that challenge. And then use that to set up some of the challenges we have to make progress on to go forward. And I'll insert one brief commercial between segments 1 and 2. So the grand energy challenge is here, and that's a dual challenge that we face. And that's really what makes it very hard. On the one hand, we anticipate dramatic growth in energy demand globally, doubling or more by end of century. At the same time, climate change makes it clear that while we're doubling energy, energy use, we need to decarbonize the energy system. So more energy, but much, much less carbon in the system. This plot illustrates the climate change side of that challenge. This is a graph of CO2 concentrations in the atmosphere as monitored on the top of Mount Mauna Loa in Hawaii. It looks at the seasonal oscillations as we go annually through 1960 up to the present. What's interesting and a little bit challenging about this graph is that in 2016, we for the first time crossed the 400 ppm mark for the full year. If you take this graph and extrapolate linearly, which is a very conservative way to do this, you would cross 450 ppm, which is a proxy for 2-degree warming in about 2037. So time is short for getting new energy systems in place that allow us to meet this increasing demand while removing carbon emissions from the system. I'd like to look at a scenario as a way to illustrate what progress we are making based on COP21 and what challenges are still going to be ahead of us even in a scenario like that. So the next two graphs, this one and the following graph, are results from a group at MIT called the Joint Program on the Science and Policy of Global Change. It's called joint because it brings together global economic modelers together with climate scientists. The model they've developed can be used, like other models, IAM models around the world, to look at different policy scenarios to see how policies can affect the global energy mix going forward, and how that impacts climate change. So in this scenario, the assumption is that all of the countries that signed on to COP21 meet the commitments they made at COP21, but don't do anything else. So after those commitments are fulfilled, they just continue at that level going forward. So that's obviously a very conservative assumption, given that the design at COP21 assumes that we will monitor progress and ratchet up commitments with time. But look at what happens if countries meet those commitments. By 2050, the world is still using 75% fossil energy sources. You'll notice that the mix between gas and coal is somewhat different. There's less coal, more gas, as we lower CO2 emissions. But still a dominance of fossil energy resources in this scenario. You can also notice from this plot that we're using more than twice as much energy by the end of the century as we were at the beginning of the century. Right? So we clearly cannot stay on a COP21 trajectory. Which we seem to be doing at the moment in an optimistic scenario. So substantial growth in energy demand going forward. If I look at the climate science predictions out of this energy mix, You, of course, get a range of possible temperature rises. The mean estimate is 2.2 centigrade by mid-century. The mean estimate at 2100 is 3.7 degrees. So this is not a curve that we want to stay on. It's also interesting to take those results and break them down by region globally. Look in the upper left corner, that's the developed world. And you see that in the developed world, energy use is essentially flat going out to mid-century, and that there is substantial reduction in fossil energy use of coal in particular going out to mid-century. What this breakdown is useful to emphasize is that this battle is going to be won or lost in the developed world, right? So all of the energy demand growth occurs in the developing countries. The other G20 countries, of course, the major economies like India and China, Brazil, Russia, they, by mid-century, will be consuming about as much energy as the world did at the beginning of this century, right? So very substantial energy growth. And we have to figure out how we can enable those economies to grow on those trajectories while getting carbon dioxide emissions out of the system. I'd like to hammer home developing countries in two particular regions. One is India, one is Africa. In India, today, we have about 18% of the world's population. 6% of primary energy is consumed in India. About 250 million people in India today lack access to electricity services. Many more than that lack adequate service of electricity. As we look out into the future, by 2040, you expect a roughly 4x increase in electrical service demand. And the sad part there is that their greatest local indigenous resource for producing energy is high ash coal. So a question we have to face is how do we help India meet that growing energy need without using all of that high ash coal? There are going to be a lot of technologies important in meeting that mix and meeting that need. Note a commitment of 175 gigawatts of renewables by 2022, which was revised a week ago today to greater than 200. And in fact, they're on a track with the tenders that they put out last Friday for another 80 gigawatts of solar in 3 years and another 30 gigawatts of wind. So they're actually on a much better path than we thought a year ago. Coal projects today in India are on hold, at least until 2020, which is encouraging also. But it's hard to see without better technology, cheaper technology, how they're going to get there without using coal. Africa has similar challenges, although further out in the future. I put that as the big challenge by mid-century. Today, Africa is about 25% of global population. Well, by mid-century, greater than 75% of their population lacks access to electricity today. Greater than 80% uses biomass for cooking. If we look out to 2030, most Africans still will lack electricity services. And that by mid-century, more than half their population, that's more than 600 million people, won't have electricity services. So large unmet need coming up in Africa that we'll need to meet. Incomes are very low in Africa, and so we'll need to meet those needs at low cost, right? And that's a challenge for us to keep in mind as we develop new solutions. It's also useful in looking at this global energy challenge to break it down into sectors. So this is a result or set of predictions from IEA, looking at, in the top picture and the gold curve in the middle there, Similar results, they're analog to the results I showed from the joint program for a world in which we meet COP21 pledges, but nothing more. That's broken down into these different sectors, and it highlights, I think, the differences and challenges in those different sectors. The power sector is the sector where we're making the most progress today. That is, in many ways, the easiest sector to decarbonize as we move from fossil energy-based power generation towards renewable energy generation and nuclear energy. There you see the business as usual scenario, which is a 4.5 degree scenario. The COP21, the 2 degree path, the green path there, is shown here in purple, somewhat confusingly, for a system in which we assume that there's no CCS. If we have CCS available as a carbon negative technology, then we can take that profile going forward. Not much difference in the time period between now and 2050. Transportation is a different challenge because we have a lot of mobile sources of emissions of CO2. Right now we're going down a path for electrification primarily in light-duty vehicles. What we do for heavy-duty vehicles is still up in the air, as is whether ultimately we'll electrify vehicles globally or whether we'll end up with some mix of technologies, hydrogen fuel cell vehicles among them. And then lastly, the third big sector in energy use is industry. There we have a different set of challenges, again, in that heat is an important part of industrial processing. Fossil fuels are particularly convenient for producing heat for process energy. How do we substitute that? Do we move from thermal processing, thermochemistry, to electrochemistry? Do we get that heat from degrading electricity? What options do we have there? So that's the challenge framed briefly. What I want to do now is give you a brief commercial. I'll tell you just in 2 slides who we are at MIT and what we're doing to look at this energy challenge. MIT's approach to the energy challenge started back in late 2006, early 2007. It was the brainchild of MIT's president, then Susan Hockfield, and her thesis was that in order to make progress here, we needed to integrate disciplines across campus, not go at this as an engineering challenge or a science challenge alone, but integrate engineering, science, policy, economics together to get solutions that would be viable in the marketplace. So we were charged with integrating across the campus, looking at energy quite broadly. So we look at energy from energy sources to how you produce those sources to how you convert them, transmit, distribute, end uses of energy, and we look at associated environmental challenges. And there are 2 big environmental challenges we look at. One of those is climate change, obviously. The other is the water-energy nexus. So there's an important linkage there in how much water we need for producing energy, services, and energy use for producing clean water. We have 3 major themes in our energy initiative: research, education, and outreach. How do we get what we learn in our energy studies out into the public discussion about policy? In research, we break down into 3 major themes: innovation, and there what I'm looking at is how do we improve today's energy systems? How do we make them more efficient and more environmentally responsible? It's important to recognize, and you got a glimpse of that in those joint program graphs that looked at how slowly we might eliminate fossil energy sources from our energy system. The energy system turns over very, very slowly because it's a multi-trillion-dollar global enterprise. If you look historically, that's also been true. Transition from wood to coal, coal to oil. Those were 60, 70-year transitions that we went through. So we will be using, like it or not, a lot of our current systems for decades to come. We have to make them more efficient and mitigate environmental impacts from those. Transformation, the development of the technologies for the future. So this suite of renewable technologies, solar, wind, biomass to energy, geothermal, and so on, plus associated infrastructure and supporting technologies, the grid, for example, storage, for example, for intermittent renewables. And then lastly, integration. It's not enough to develop these individual technologies. Ultimately, consumers look at energy as a commodity. They want a service. When you plug in your cell phone to charge it, you just want it to charge, right? You don't care about the individual technologies that got those electrons to you. So we have to think about the systems integration of all these different technologies. I put a few numbers up here just to give you a sense of what we've done in the 10 years since we started our first research programs. We now engage probably closer to 350 of MIT's faculty in our energy program. MIT has 1,000 faculty, so that's 35% of the faculty. Many of those don't do this full-time. They have other programs they work on, but it's a really important reflection of how you bring different disciplines to the table and how important that is in making progress. We've brought in better than $660 million so far in funding the initiative. Most of our support is industrial support. I should say that from the outset, our thesis was we should partner with industry closely because we felt that industry was important for helping us understand what the high impact problems would be, which ones would make the biggest difference in the marketplace. And secondly, given the scale of the energy system, industry is essential for commercializing and scaling up these technologies to impact our global energy system. So industry's been a key partner for us from the outset. We have now some 90 industry and public partners, but mostly industry sponsorship. About 2/3 of our budget is industrially sponsored. That's probably the flip of most university sponsored programs. The second largest part of our sponsorship is philanthropy, and by far the smallest for us is government, and that's a very good thing in the U.S. Today. We've funded close to 1,000 research projects so far at MIT. More than 160 of those were seed fund projects. That's been an extremely valuable way to get young faculty to look at energy challenges and to get faculty from disciplines that haven't traditionally been involved in energy to get them to the table and bring their expertise and new ideas to the table. So that's been very helpful. And MIT has spun out more than 60 companies, startup companies, in the energy space since MIT launched. And they cover the gamut from new solar technology companies, new battery companies, to software companies that look at how to help users identify how they consume energy and how they might do it more efficiently. That's the commercial. So now back to the challenges and what we've been doing lately to address these challenges. And by lately, I mean the last 35 years or so. So I'm going to give you two examples. One of those comes from the fossil energy sector. The other comes from the renewable energy sector. In fossil fuels, a big story has been the production and the penetration of shale gas, and more recently shale oil, in the energy system, particularly in North America. This is a graph that looks at shale gas development in the blue curve. And you'll see the growth of gas in the U.S. Up until about 1973 or so. Then the dip in gas production, we had some very high spikes in gas prices in the 90s. And then finally the increase in gas, rather dramatic increase in gas, post about 2006. And that's when shale gas production started to take off in the U.S. Now I say that this is a 35-year story, not because this is when you see the penetration of gas and the growth in gas production, but because the research that enabled that went back at least 30 years. And it included 3D imaging technologies that helps you drill through these layers with precision. It included horizontal drilling technology, and it included much better fracturing technology. But that's unlocked a resource we didn't have. It had a dramatic increase in the U.S., which I illustrate here, through the production capacities of some of the biggest shale plays within the U.S. And I call your attention to one in particular. This is the so-called Marcellus shale play, which is in the northeastern part of the U.S. It's Pennsylvania, Ohio, western New York, West Virginia. And that is a region that you don't normally associate with oil and gas production. But if you look at the production there today, it's more than 6.5 TCF of natural gas. That's more than Canada or Iran or Qatar alone. So it's a very large single play in the U.S. The largest gas field or shale oil field in the U.S. is just now starting to be produced. That's in West Texas, the so-called Alpine High field. So that is a large resource that we didn't have. Those technologies have changed the supply cost curves in those areas. One of the consequences in the U.S. has been a rather dramatic decrease in our CO2 emissions over the last 17 years. And I think you can trace that back exactly to this substitution of natural gas for coal in our energy mix. As natural gas has become more plentiful, prices have dropped, and that market effect has been what has driven the swap in gas for coal in our electricity generation system. It was not the war on coal that Obama ran, as you may read in the press. Today it's simply a market effect. And so this better technology in fossil energy has led to substantial environmental benefit. This is the largest decrease in CO2 emissions from any single technology globally, right? So a great story there. But it points to a greater challenge down the road, which is eventually we will come, sooner than later, to the point where even gas has too much carbon in it, right? So this is a great intermediate pathway, but it's not the answer going forward. We have to keep that in mind. Second story is solar, and that's been a really dramatic story globally. This looks at investments in solar around the world over the last 6-7 years. In 2016, for example, if I pull out North America, the U.S., you can see some 20 gigawatts of solar and wind together that were put in place, capacity, not production, and more solar than wind. Why has that happened? What's driven that has been decreasing costs of solar, of course. If you look at, oops, whoa, I have to look really fast there. Yep, here we go. So if you look at PPA prices in the U.S. From 2006 to today, you can see in these graphs the size of the bubble in each of these points is the size of the installation, the capacity of the installation, and the height on this curve tells you what the PPA price was. What you'll see is, of course, this dramatic decline, which has been driven by decreasing solar module cost, but also decreasing costs of actually installing solar. In 2016, in the US, there was a PPA in Nevada with Nevada Power at 3.4 cents a kilowatt hour, which for the US is quite low. In May of this year, there was a PPA signed by Tucson Electric for 4.5 cents a kilowatt hour, which is very impressive if you consider that it includes storage. So that PPA was a 100 megawatt PV power plant with 120 megawatt hours of storage, 4 hours of 30 megawatts of battery storage. So we're getting to the place where there are competitive PPA prices, even including storage. And of course, if you look around the world, the best PPA prices today, probably Saudi Arabia a month or so ago at 1.8 cents a kilowatt hour, Mexico at 1.7 cents a kilowatt hour. So some really interesting prices. That's the good news. The challenge going forward is that as we get more and more PV or solar in our system, there are challenges with cost and with system behavior, system operation. This looks at what happens to the average price for electricity and the value to the asset owner for solar as solar penetration increases from 0 out to 36% in a world without storage, right? So we assume for these projections that there's no storage available. And of course, the challenge is that you have a lot of solar production midday, right? And that can go in and first meet peak demands, but ultimately you have solar bidding against itself when you get large penetration with the result that the value and the prices you can receive go down to 0 or below. We've experienced this in parts of the US. Germany has experienced that. Any region with large solar penetration has seen that already. So that's a challenge for solar without storage. A second challenge is the system behavior. This is a look at a part of the US electrical system called ERCOT. That's basically the state of Texas. We use them to study because it's more or less an isolated system. Texas loves to be isolated from the rest of the world. There you look at the way we meet load in Texas over a typical day. So the orange or red curve on top is the total load over a period. I laugh that the students that did this have a 30-hour day. Graduate students at MIT work harder than anywhere else, so they get 30 hours in. But I had them put in a line at 25 here, so you have a 24-hour day for comparison with others around the world. What you'll see is that, of course, if there's no solar penetration, then you meet all of that demand on top by non-solar generation resources. With 12% solar, then the yellow shaded region is the part of that demand you meet with solar, all in the middle of the day, and the brown part is what you meet with non-solar generation. Note that the peak demand was about 78 gigawatts. If you look at and all that would have to be met with non-solar generation with no solar. With 12% solar, that goes down to about 70 gigawatts, right? So I still need 70 gigawatts capacity that's non-solar in this system. Now look what happens as I go out in solar penetration. The amount of solar that's going into the system increases. The yellow part gets bigger, but the peak of the brown part doesn't change, right? So I still have to have the same capacity of non-solar generation to meet off-solar peak hours in the system. And a system challenge we have is who pays for that, right, going forward. The other system challenge here is that I have to ramp faster and faster to get back up to that peak after the sun starts to go down or starts to move through the sky in the afternoon. Now, this is a look at some of the EIA data for prices in California. I put this in just to show that prices do go negative during the middle of the day in California. You can see similar results, as I mentioned, in other parts of the world. So we have good news with solar. Prices have come down. Solar capacity globally is going up, but is still small. There are challenges in meeting our energy needs with solar if we don't have storage. And so that points, with the shale gas story, to a number of challenges going forward. And one of the ways we're going after those at MIT is through a set of what we call low-carbon energy centers. So these have been set up to focus on 8 key technology areas that are going to be important in meeting this projected global energy demand. They range from, at the upper left, CCUS. So how do we deal with gas or other fossil energy systems as the gas or other fossil source has too much carbon for our climate constraints? At the bottom right is solar energy, which we just talked about. How do we lower the cost of producing that solar energy so that we can compete with these ever lower costs that the provider can receive in high solar times of the day? Energy storage is clearly a key area. We saw that in these last couple of slides on the impacts of increasing penetration on the system behavior without storage. So I'm going to pick a few of those and talk about some examples of work that needs to be done and what we're doing at MIT in these areas. The first one I'll pick is this CCUS, because we have a lot of fossil energy production today, and we need to get the carbon out of that. The most expensive part of CCS is actually capturing the carbon in the system. The upper left in this curve is a typical system for doing that. The technology of use today is an amine capture system. Amine will grab a hold of CO2 and hold it tightly. But in order to recycle the amine and make this process affordable, I have to get the amine to let go. And I do that by going from the scrubber to a desorber. The way I convince the amine to let go of the CO2 is I heat it up. And I have to heat it up to about 110 degrees centigrade. To do that, I have to replumb a coal-fired power plant or a fossil energy power plant, take steam and use it to heat this amine CO2 complex up and get it to let go. That's expensive to do, and it takes steam away from making electricity. So it's costly to the power efficiency of the power plant. One of the ideas out of MIT to address this is to add a third component to this system. So add a divalent ion, say copper +2, to the system. Amine still grabs the CO2, but in the presence of the right electric field, the amine will prefer this copper ion to the CO2. Right? So it'll grab the copper ion and let go of the CO2. That's a very cheap process to put in place. You just need to put in, expose the solution to this electric field. No replumbing of the steam lines is needed, and there's no parasitic load on the power plant to do this. Right? So this promises to be maybe 50% less costly than the traditional amine capture technology. So we're looking forward to seeing that and other ideas for lowering costs of carbon capture going forward. Thermal power plants produce about 85% of the world's electricity today. At the back end of every one of those power plants is a condenser. The condenser, of course, takes whatever residual steam there is, converts that to liquid water so it can be run back through the process. Typically, those condenser surfaces get dirty. When they get dirty, you get a film of water on the surface when it condenses. That film of water gets in the way of heat transfer, right? So you have a very inefficient heat transfer coefficient. This is an illustration of technology developed by two faculty at MIT, Karen Gleason and Kripa Varanasi, which coats the condenser surface, uses a CVD technology to do that, coats the condenser surface to make it very hydrophobic, so you force dropwise condensation. With dropwise condensation, as shown here, I get a 7x improvement in the heat transfer coefficient, which is an amazing improvement in the condenser efficiency. Overall, for the power plant, you probably get 1–2% improvement in efficiency. But given how many thermal power plants there are in the world, that's an opportunity for an incredible reduction in CO2 emissions. Materials opportunities abound in the energy space. Another example, again from Kripa Varanasi, is a technology for capturing moisture from cooling towers in thermal power plants. He's developed a wire mesh dome you can put over the top of the cooling tower. It uses electrostatics to attract the water droplets to wire, which is super hydrophilic, and the water is wicked along the wire to be collected. He can collect about 95% of the moisture from the exhaust in the cooling tower in a thermal power plant. Very little parasitic load on the power plant to do that. If you're in a coastal region and use salt water for cooling, as a benefit here for free, you get desalinated water. It's a very interesting technology. I think MIT, as part of its Plan for Climate Action, is actually trying this out. We're currently in the process of retrofitting our power plant to try out this water capture technology. I mentioned that solar is obviously the big opportunity for meeting energy needs globally, but we need to make it cheaper. One way to do that is with new materials for solar in formats that are cheaper to manufacture, easier to install. This is a look at the world's lightest weight solar cell. This sits on top of a soap bubble here, a work out of Vladimir Bulovic's lab at MIT. I don't think we're going to install solar on soap bubbles globally, but it points the way to new technology for making solar even cheaper than it is today. The capital cost for building plants that could make these solar materials is much, much less than silicon wafer plants. And so that's an opportunity. How that's going to shake out relative to silicon is yet to be seen. Battery technology, I mentioned, is a key technology going forward. This is a look at a team that just spun out a company called Baseload Renewables. This is Yet-Ming Chang and some of his group. Yet and his colleagues published a paper in Joule a couple of weeks ago, which had some interesting economics on storage technologies, comparing the DOE target for $125 a kilowatt hour storage to the cost of the chemicals you would need to make that target. They come up with a number of about $1 for the total cost of all the chemicals that go into the battery if you're going to, through the manufacturing process, end up at 125. Lithium ion doesn't come close to $1 for all the chemicals. So he's looking at, and others around the world are looking at, a variety of chemistries that would let you get to really cheap raw materials for the battery. This baseload renewables battery technology is based on a flow battery configuration, uses a chemistry with sulfur as a major component. Sulfur, at least at the moment, being very, very cheap. Last example I'll give is one of nuclear. This is a group at MIT led by Dennis White, our Plasma Science and Fusion Center, looking at fusion. And could we do fusion cheaper and sooner than probably everybody in this room thinks is possible? They use the same physics as is used in the ITER program, the big fusion reactor that's being built outside of Marseille. But unlike what's different between their technology and their design and ITER is that they have high temperature superconductors that allow them to get to roughly 2x the field strength of the magnets at ITER. And since the fusion power goes like the fourth power of the magnetic field strength, you can get a significant reduction in reactor volume. That they believe will enable them to make a test reactor much sooner, much cheaper. They're currently in the process of making these magnets. They hope to do magnet tests in about 3 years. If the magnet test proves positive, they think they have a clear path to a test reactor they call Spark in about 10 years. So I think there's some interesting possibilities in fusion that we also ought to keep an eye on. My last two slides look at system issues and developing countries. I mentioned earlier that it's important that we not just look at technology, but understand systems. I show as an example of one of the studies we've done recently, this one called Utility of the Future, looking at the system challenges to regulators, challenges to businesses who provide these services, as we get more and more distributed energy resources on the system, as we get more and more digital technology in our system, as our transportation system gets more electrified, that impacts the system. A whole lot of changes happening in this sector, and we're trying to tease out how those will play out in the marketplace and how they will play out in different parts of the world. So a goal of this study, and what ended up as a major report, is a toolbox that enables regulators to understand how to most cost-effectively help distributed energy resources enter the electricity services sector as we go forward. That study and that understanding was the basis of one of those 8 low-carbon centers I mentioned earlier, the Electric Power Systems Center. There's currently a study like that underway on mobility of the future study, and after that we will probably look at that third sector, the industry sector. Last slide, I want to go back to developing countries and end here because, as I said earlier, I think this is where we win or lose the climate change battle. This is where the growth in energy use is going to happen. This is where emissions growth is going to happen or not, as that energy use grows dramatically. To address that and to help us learn how to address that, we launched about 5 years ago a center at MIT called the Tata Center for Technology and Design. This is funded by the Tata Trust, and it's fundamentally about how do we teach students to go into an area, a developing country like India, identify unmet societal needs, and figure out how to meet those needs with technology. Energy is an important piece of that, obviously. We have, at any one time, maybe 50, 60 projects going on in India. One of the pictures I showed, I had a little inset on the soap bubble that I had this very lightweight PV on. That was a picture of one of the Tata students, Katie Steele, who had developed a solar-powered irrigation pump that meets irrigation needs for rural farmers in India. So it's a 31 million customer market in India. By redesigning the pump, she could take advantage of the shallow water table in India. She gets a 1-year payback on this pump relative to a diesel-powered irrigation pump. But finding out how we can go into a country like India and meet its growing energy needs is going to be critical for our future. We've expanded now, based on our work in India, we've expanded into sub-Saharan Africa. We have programs in 8 different sub-Saharan African countries today. So with that, I'll stop, and I thank you for your attention.
Thank you very much, Professor Armstrong. If we could open up the floor to questions now.
We've solved the problem. There you go. One of my points was that we haven't, and you'll read some places in the literature that we have solved the problem, and I firmly believe that's not true.
Thank you very much. We could all thank Professor Armstrong, please.
Yeah, let's all round of applause for Professor Armstrong. If
Sorry,
you could
we
take
do have one question.
If you could take the floor again.
So, right, Marcus Kraft, University of Cambridge. Bob, thank you. I thought it's a very enlightening talk, but I'm also a little bit depressed, okay? Because your future projection for energy consumption and the use of fossil fuels didn't go down. It went up, okay, despite everything you said. Can you comment on it?
This was a talk about challenges. So that is the challenge, right? Is we have to get technology solutions that are cheaper. I didn't talk about policy, but we need better policies, clearly. I feel quite strongly that we need a price on carbon that's global. I think there's some ways to get there. We've actually talked about that. So I think unless we have a substantial price on carbon, so that we can reset the marketplace and let the market develop efficient solutions, I think it's going to be very, very difficult to get there. Heike.
Yeah, Heike Weber from BAS, Berkeley. Honestly speaking, I like everything what you said, but it is just for us to use this as the challenge, because really, I think things can go much, much faster than you predict. I think we can be more disruptive in the transformation from fossil fuels to renewables, driven by the market, not driven by carbon tax and by the climate. And I think really, if you look at what Tony Seba says with the disruptive nature of this transformation, which is much faster than anybody expected. You know, Tony Seba shows the picture that in 1980, it was AT&T, Bell Telephone, made a study with McKinsey, how many mobile phones will we have in the US in 15 years? And the result was we might have the stunning number of 800,000 mobile phones. It was 100 million mobile phones. So I think we are really here looking at a lot of linear extrapolations that do not take into account the self-accelerating power of disruptions. You know, now that we can have solar electricity in Mexico, not in Abu Dhabi, for 1.7 cents per kilowatt hour, this shows that we are in a process where what happened up to now is accelerating what will come. We have exponential growth of solar. We expect in 2030 to have about 3,000 to 5,000 gigawatt already installed. So I do hope that what you showed will wake up people to say, this cannot be our future. It would be a complete disaster for the Earth. And of course, I hope that the disruptive nature of the low-cost renewable energies. We don't need to further bring down the costs. You know, in Germany, they had the crazy idea because PV is so cost competitive, they slapped a tax. We increased the cost of PV in Germany by 1/3 with the solar tax because they were afraid that we too quickly changed to renewable energy. So I think, I hope what you showed will be just the bottom line, the threatening case if these disruptions don't take place. But let's see and talk again in 5-10 years what has really happened.
So just to emphasize, the graphs I showed of projections going forward, that was a scenario based on what we have agreed to so far, right? Which is clearly insufficient, right? That was part of the message there. So challenge is, how do we get the technologies, the markets, the business structures so that we can do much, much better than that. So the countries are actually willing to go there. And that as countries put more stringent policies in place, we have a toolbox that enables us to get there. I hope you're right about the penetration looking like cell phones. I tend to worry that the cost, the capital cost of these big energy systems is much different than what we saw in the telecom build out. So I think that's wishful, and I hope it works out that way. But I think that and that's actually been a problem in startup companies in energy. The capital you need tends to be much larger, and it needs to be there for much longer periods of time. So that was the thesis at COP21, this group, the Breakthrough Energy Coalition, right? Their idea was to get wealth together that was willing to apply patient capital to some of these energy technologies. And that we're just now beginning to see the start of that, right? So good point, yeah.
Would you say that if a CCS technology will be developed, we can go back to fossil fuels? And if so,
I didn't say that, but
that's why I asked.
Yeah, no. So that's a fair question, because I think in the end, it will be a market decision, right? Mm-hmm. If gas plus CCS, however you do that with gas, is cost competitive with solar plus whatever firming technology you need, whether it's batteries or something else, then you'll use the gas with CCS until it gets more and more expensive to produce gas, right? But let the market figure that out. I have a problem with coal in that coal has other problems besides the CO2 content, right? I mean, there are a lot of criteria, pollutants, and so on with coal that I worry that if we went back to coal at large scale, we would have some other environmental disasters to deal with. If you scrub all of that and include that in the price, fair enough.
Mm-hmm. Then why not to focus on the CO2 capture?
Look, I mean, one of the things that I believe DOE in the U.S. is doing right now is at least stating a new focus on CCUS, right? And I think we should. I don't think we should be taking any options off the table at this point. We do it however it's cheapest.
Right, I shouldn't ask two questions, but I do. Sorry. Okay, I'm between you and the dinner, the lunch, I suppose. Okay. So the question is, okay, why do you want to do carbon capture after you have combusted fossil fuels? Why don't you capture it before you combust? Okay, because the cost of separation is enormous, right? And there is no need to couple the two things. So are you looking into this?
Absolutely, but you might want to talk to the Southern Company about that, right? They just walked away from the Kemper project in Mississippi. That was too costly. Exactly right. Now they say they have the technology working. That was $5.5 billion, $6 billion for a 600 megawatt coal-fired power plant, and they were going to capture 60% of the CO2. It was a gasification project. Again, I think we should be looking at all of these technologies and see if we can find breakthroughs that make them cheaper and let the market sort out which ones to use. And what you need in different parts of the world will be different. Some parts of the world have good coal resources, natural gas resources. Others are blessed with great hydro resources or solar resources. So, you know, what this is going to look like in different parts of the world will be dramatically different.